Phase diagrams are like a map of the phase of a substance, the phase or the state, solid, liquid, gas, and looking at that as a function of pressure and temperature. And so in a phase diagram, there are regions and there are lines. The regions represent a set of conditions where that particular phase is stable, and the lines, or they're usually curves, represent a set of temperatures and pressures at which that state change is going to occur. And so there's a line or a curve for vaporization, one for sublimation, and one for fusion. And there's a unique set of conditions called the triple point. And the triple point is where all three states are stable and in equilibrium. So you can have the gas, the solid, and the liquid all present together. That's weird. Yeah, it is. It's weird. So this is a demo using tertiary butyl alcohol. And they're pulling a vacuum on it. So they're lowering the pressure, and there we got to the point at which it boils. You can get water to boil at room temperature. So there it's boiling. That's 30 seconds after the start. Two minutes later, see that? It's starting to freeze. That's a solid forming. But wait, it's boiling too. It's boiling and freezing at the same time. Is that weird?
That's pretty cool.
That is very, very cool.
I guess we're not gonna do anything like that.
Unfortunately, it requires a pretty significant vacuum pump.
Oh.
So, yeah. But we've got this great video, right? Oh, come on.
It's like the guy in space with the water and stuff.
I'm sure you're going to say, well, why didn't you take us up on the space?
No, that one, no, thank you. I am perfectly fine on ground.
Yeah, I'm not planning to leave Earth.
No, thank you.
I'm an Earthling, proud of it. Okay, so that is the triple point. So this is what a phase diagram looks like. This is the phase diagram for water. This is the triple point for water. This is not to scale. So you have to get, you have to lower the pressure and get the temperature pretty low to get the triple point. But this is the fusion curve. So this is where we go from a solid directly to a gas. This is the gas region. This is the liquid region. This is the fusion curve where we're going from a solid to a liquid. Vaporization curve going from from a liquid to a gas. And this is the critical point. And above the critical point, there's no difference between gas and liquid. It's a supercritical fluid. So we talk about navigating a phase diagram. And so you can look at, well, what happens if we go at a constant pressure and we're going to increase the temperature? What happens? Well, if we're starting at a temperature at which it's a solid, as we increase the temperature, it's going to melt, right? And then at some higher temperature, it's going to boil, vaporize, and become a gas. Or we could look at, well, at a constant temperature, what happens when I change the pressure? Well, if I take my normal pressure and I reduce it, at some point, it's going to turn into a gas, even though we're still at room temperature. This is one of the very vivid memories I have from high school chemistry. Beginning of lecture, instructor had a big vacuum flask with some water in it, and he turned on a vacuum pump, and it's just sitting there chug, chug, chug while he's lecturing. And after a while, the water started boiling. It was just a flask sitting on a black bench like this one. And then he made us all come up and touch the boiling water. It was room temperature. It just boggles your mind, right? Because boiling water is hot. Not at low pressure, it isn't. Water can boil at room temperature at low pressures. Just, crazy. So, normally this fusion curve has a positive slope. This is iodine and carbon dioxide. If we go back to water, water has a negative slope. That's unusual. Because what that indicates is if we have, say at this temperature here, if let's say, what am I doing? If I have this temperature and I increase the pressure, I can cause the solid to melt. Most things, if you increase the pressure on a solid, it just stays solid. If you take the liquid and increase the pressure, it will freeze. Water is backwards that way. That's why ice skates work and sled runners. An ice skate, I mean, the blade looks pretty narrow, but it actually has two little edges, right? So if you look at the end of it actually goes like this on the bottom. And so it's got these two edges. And so all of your weight is on those two really thin edges. That's a lot of pressure on the ice. And that's enough pressure to cause the ice to melt a little bit. And wet ice is much slipperier than ice that is not wet. And so that causes a little bit of melting, which lubricates the ice, and that's why ice skates allow you to glide around. Well, they make it look easy. It's actually not that easy. So that's something. And then the weird thing about carbon dioxide, at 1 atmosphere, it goes from a solid directly to a gas, and there is no stable liquid state for CO2 at atmospheric pressure. You can get liquid, but you have to go up to above 5 atmospheres, which is pretty high.